I want to acknowledge, since I'll get lost in what I'm talking about, the collaborators for these two other papers. The paper that I guess this talk will most center on is a collaboration with Alex Choldachova, who's a fantastic colleague at Heinz School of Public Policy at Carnegie Mellon. And my most recent work in this area, which is just posted, is about algorithmic fairness from a non-ideal perspective and making a connection between political philosophy literature and sort of a lot of the things that I think are going wrong in the fair ML literature. And this is work with my postdoc, Sina Fazalpour, who I'll shamelessly advertise is a potential job candidate, and I think is absolutely wonderful collaborator. And I think anyone with a position to hire him should. And I think he's one of a true interdisciplinary scholar in this area. So here's the kind of, if we review the here's the like a million miles out, zoomed out pattern that I think we keep seeing over and over again. Is what people do is they take a problem that's not really a prediction problem, and they fashion it as a prediction problem anyway. So they come up with a surrogate. They say, what is something that, I'm trying to make some kind of decision. What is something that I have a label for that in some way has the same shape as the kind of action I'm trying to take? What is some available covariates that I have for trying to predict that thing? What is some statistical measure of success, say, something like accuracy? This is all assuming that we have a prediction task, even assuming that we have a well-defined probability distribution, right? Accuracy, I think a lot of times in this conversation, people come up and say, well, if your model is super accurate, why do you care about interpretability? Why do you care about fairness? Why do you care about whatever? And the problem is that accuracy is, it's not even clear what accuracy means a lot of the time. It's a wrong problem, and accuracy itself it's an expectation. It's the expectation of, indicator function of your prediction equals the true label. An expectation is only well defined with respect to a specific probability distribution, and a lot of times we don't really know what data generating process we're talking about. Then, right, some trouble arises due to the fact that we basically haven't posed the problem correctly. And it's not just an insufficiency in the sense of like the sort of insufficiency that machine learners are used to dealing with. As machine learning scientists, you're used to dealing with the insufficiency of your predictive performance is lower than you have reason to believe it could be. So I want higher accuracy. Here, I think we have insufficiency of a different kind. I think this the sort of kind that statisticians are a little bit better at thinking about, and I think people who think really deeply about the science or philosophy of causality are crystal clear about thinking about, which is insufficiency of language. Like you fundamentally don't have the right technical language for describing the problem. And so in this case, right, there's no way, people have tried for a long time to describe causal effects purely in like naive ways as statistical quantities, and they're not. There's a richness missing from the language. You need actually a notion of the counterfactual, whether you define that in terms of potential outcomes or the do operator. In this case, I think there are some deep connections to causality. I don't want to overemphasize causality, but I think there's a similar kind of like pattern of the actual language in which we're trying to cast the problems is insufficiently rich to describe it. And what happens then is we have a set of people with a toolkit that they use to create a product. The insufficiency of that toolkit gives rise to a problem, and they say, well, let's use the toolkit and try to fix it. So what are the tools of fixing things? Adversaries, regularizers, the kind of standard handful of things that sort of naive machine learning practitioner knows how to do. And another thing I'm going to, since I guess we've got 2 hours, I can really ramble, that I point out is, another kind of, I think a fundamental issue here is that the people who are building these tools are generally machine learning scientists. One thing that machine learning scientists are really good at is getting results of predictive performance. One thing that we spend almost no time thinking about is identification, right? And this is something that people who are experts in causality are really good at. It's a question of, do you even have the right information to answer the question you're asking? Because if you're always asking the question, what is the best among the hypotheses in my hypothesis class, that's a question that always has an answer, and it's an answer that's estimable from, because you've taken as given the observable data. You've taken as given the hypothesis class. Say, how can I find the best one? Causal effects, they might not be identifiable. If you just show me, observed data of x and y, no one can say just by looking at the joint distribution over x and y whether x causes y or y causes x. The problem is fundamentally underspecified, right? And so this is something I think no one in the ML fairness community is, I think, adequately addressing, is stepping back and saying, do we actually even have the right ingredients in a lot of these cases to make, to have the sort of normative guidance that we need to be able to make the relevant kind of like moral determinations. So we have this mistake of like trying to solve the problem, but the solutions are fundamentally flawed in precisely the same way that the initial products were fundamentally flawed. And then what we do is we mislead the public and tell them we've solved it. So we've got, you write a paper and you say, this algorithm is fair. And the reviewers don't see it usually as their job to address like this kind of claim. They'll say, well, let's look at the algorithm. Does it look technically sensible? Do I like the graphs? But we sort of have a sort of slippage. The review system is not stopping people from making these kinds of claims that basically, in general, this is a cancer of the AI community, right? Because we've done this since the beginning of time. We do it with lots of things. We do it with intelligence. We do it with consciousness. We do it with the word understanding, with comprehension. There's a great paper from the 1970s, maybe. I don't know. I wrote a paper called Troubling Trends in Machine Learning Scholarship a couple of years ago with a statistician at Berkeley, Jacob Steinhardt. And at some point, we were detailing a number of sort of problematic patterns we see in papers, and we reached out to people to get some, we realized we were maybe committing career suicide by writing this paper, especially because we were very citey. And one of the pieces of feedback we got from people was, well, is this really unique to machine learning, and is this really unique to now? And this, we spent a few weeks going and digging through and this is a recurring cycle, even within machine learning. And then there's a paper from the late 70s or early 80s in the expert systems days, like around maybe just before or around time of the first AI winter. I think it's called Artificial Intelligence Meets Natural Stupidity. And even back then, they're saying, hey, if we ever solved language understanding, what are we going to call it? Because that name's already taken. Same thing with, by something that's not understanding. And same thing with, I think, a lot of things, like even basic kind of logical reasoning, things like the word deduction was overloaded to mean something that wasn't deduction. So, this is a pattern that we have. But I think the danger here now is we're actually building real products that people were using, and we sort of are putting these academic certificates of like, we've solved it. Like we have a model and it is interpretable. And there's a whole system of incentives to sort of say, hey, no, we are working on this problem. We've got tools. And to give you a sense of what's gone wrong is like you see this, can I say the word shit or no? I'll say stuff all the time, but like, I don't even remember who this is from, but this is, from some company using machine learning for hiring, and they attest we have bias-free algorithms. I don't remember if this is the one. This might be the one, at least one of them is there's a company called Pymetrics out there. And Pymetrics, basically what they do is they said, oh, I saw this 4/5 rule somewhere. Let's just test whether or not we're complying with the 4/5 rule. Now, I think it's very easy to design a real-world scenario in which aiming for something like the 4/5 rule is progressive. I think it's very easy to design a world in which it might be like something most people would think of as the very most racist thing you could do in a given situation. But they just say, hey, we comply with the 4/5 rule. This is bias-free. Like, academic scholars and top, MIT and all over the world are said this is the definition of fairness. Or here's an example of, I think, dangerous solutionism is, on Twitter, someone at a large prominent tech company, who I shall not name, but the company rhymes with frugal, was sort of called out on Twitter on account of some of the impacts of some of the services, the data-driven services. It says, hey, look, you think we're not dealing with this, but the field's more sophisticated. Like, there's many excellent papers on bias. Like, this is the problem. Like it's like sort of like, hey, we've got this. We've got a team working on fairness. And the real danger is that, and what I'm going to get to, ultimately is that I think the real danger is that what we could do is just sort of preserve the status quo, deploy products that are absolutely flawed in the same way as the ones we're concerned about, that sort of function in qualitatively like the same exact way, but to call them fair and to create sort of a like shield against the sort of more thoughtful regulation that's actually sort of called for here. So I know we've got an interdisciplinary audience. I apologize if this seems, a bit ABC. So I'm going to kind of just like, let's look at what actually is happening in machine learning at the most basic level, and then kind of put it, maybe juxtaposed against what I think is actually demanded by these settings that we're entering. And I think it'll become clear what some of the problems are. So basically, we have one hammer. I think if you go to a machine learning conference, you'll believe we've got 4 or 5 hammers. But if you work in industry, you know that we have one, right? And that is supervised learning. It is the only thing that we know how to use to turn data into products, right? At least in terms of like data-driven like automation. And the setup is really simple, right? We feed some data into a function called an ML algorithm or supervised learning algorithm. It ingests a data set, a collection of inputs, and something that we've decided to call the output. These collectively, the data set of the inputs of the machine learning algorithm, and its output is a function that we call the model. And the model, we hope, if it's learned to generalize, which is no trivial feat, and it's something that, and we still don't even know why neural networks generalize. The output of this is a model that, if things have gone well, we hope shown a new input from the same distribution. This model will sort of, in expectation, have low error at predicting what is the corresponding target. And so, we come up with things. We say, oh, we've got a big number of examples of this is a sentence in English, this is a corresponding sentence in French. We'll put all these sentences together. So these could be really complicated objects, but at the end of the day, that's sort of all it is. We've got neural networks, which are just one way of expressing a family of models. That's all it is. They're loosely neurally inspired. This is really a name that owes more to legacy than any kind of biological plausibility, because they were really invented by McCulloch and Pitts, who were psychologists, and actually were interested in cognitive science. And recently, people have gotten excited about deep learning, but the fact that it's deep really has no bearing on the conversation here. I think this is a big distraction, and I think the entire interpretability discourse has gone, I think, has really misled people into thinking that the important issue is whether the model has 2 layers or 10 layers or 20 layers. The problem is that we're expressing everything as a statistical prediction problem. And that problem doesn't go away if you're training linear models. And the fact that we're doing deep learning really has no bearing on the conversation, I don't think. That's my opinion, though. But I'm speaking, so I guess I got to say that out loud. So, right, all we're doing in building these products is curve fitting. This is a point that I think for anyone who doesn't have a background in causality, I really recommend reading this book. These are some quotes from Yuta Perl when he was on his sort of like victory lap, press tour, promoting the Book of Why. It's a bit snarky, and he does certainly give a few sucker punches to his long-held grudges in the statistics. But it's also a very, very readable book, and I think I approached it at the time with almost no background in causality, and found it, it makes a lot of, he's a great explainer, and I think basically his point is to say, hey, machine learning is stuck entirely on learning associations, and some things are just fundamentally not associational quantities that we're interested in. So treatment effects, for example, or a classic example of this. And there's sort of like 2 sides of this. Like, the one side, which I think he concedes, is, hey, we did not expect that so many problems could be solved by curve fitting. So I think the fact that you can get, maybe we haven't really truly solved translation, and maybe we even can't fundamentally with a purely associational system but we can get it to the point where it's useful enough to people that it facilitates like global commerce in a way that like otherwise wasn't possible. It can't, to the point that it actually does significantly erode a language barrier. Like we have these great results that people are really excited about, and yet at the same time, while sometimes that's enough, it's just fundamentally, often just not what we're interested in. So I kind of stole the title for this slide from a workshop, a really great workshop that Cynthia Dwork ran at the Simons Institute called Wrong at the Root. But basically, the problems we're addressing, the problem is that they're usually not just supervised learning problems, right? So almost all the time we're interested in automation. Automation concerns making decisions, concerns taking actions, and we're usually interested in the effects that those actions will bring about. Now, what we usually do is we just say, well, let's just train a machine learning system and that somehow we think there's some kind of loose connection between the prediction problem and the causal problem we're actually interested in. Let's just throw it in the wild and see what happens. That's what happens. That's the state of the art in industry. And this plagues every system, even ones where we just don't worry about it because we don't think there is some important moral consideration. So like recommending products at, say, like large retailers, what do? They just predict what people, based on, say, all their purchases up until a month ago, would purchase in the succeeding month. Now, is that actually, like, how is that connected? Like, what you really want to do is show recommendations to people that either are going to uncover products that they want to buy, products they wouldn't have otherwise bought. You want to have some effect on their level of engagement, the amount of time they spend. So even from just a purely profit-seeking mode, you're solving the wrong problem. But that's what we're doing, right? Is that we say, well, let's just predict what they would have bought, use that to populate the carousel, and then what you do is, where they at least get a little bit of a flavor of causality is not in designing the tool, but in evaluating it. What no real business actually says, oh, you got a great AUC, let's deploy this for 2 billion customers. What they do is they say, let's run an A/B test, which is basically a randomized controlled trial. So let's try this sort of incoherent thing against the previous incoherent thing that we had, but at least we'll be a little bit coherent in at least the short-term effects of it by just kind of monitoring in the wild and see what happens vis-a-vis their like inevitably like kind of profit-oriented kind of metrics of interest, like how many people signed up for your site, how many people joined your loyalty program, how many purchases did people make. So, what I'm going to argue here is that the literatures on fair algorithms and interpretability are kind of, I think if you look at what people say they're going to do, you look at a typical interpretability paper, they say, we're using this to make decisions about criminal justice, we're using this in medical situations, where how do we know if the model's robust, how do we know if the model is going to hold up if the data distribution changes, how do we extract causal effects, and say, so let's make it interpretable, or like let's add, or if it's a fairness consideration, let's make it fair. What they never stop and ask is like, are these questions that are addressable within a supervised learning framework? And I think they often aren't. And I think interpretability of the case is really clear. It's because they mainstream papers are purporting to tell you something about robustness, and this is a field that like actually is quite mature and has deep connections to causality, because you basically say what makes your future data similar to your past data? In what ways are these distributions linked? If they're not linked at all, if you make no assumptions about how those distributions are similar, then basically training robust models is fundamentally impossible. There's no free lunch. You have to assume something. Usually what you assume starts looking like causality in the sense that you assume there was some alteration to your data generating process that makes the future look different from the past, which is something that looks like an intervention. So, so we come up with these sort of hacks, and we publish papers, and there's a little bit of a market, I think often by well-intentioned people, of like the people want to consume these papers, they want to encourage work in this area, but the result is that people get away with absolute murder and publishing papers that truly make no sense, and the real danger is that we can give the appearance of a solution. So I want to go even a little deeper and say that even if I don't think we're addressing prediction problems, but even if we were, there's already situations where we would start to worry about bias in the context of, say, disparities among various groups. Even before we start thinking beyond the umbrella of prediction. For example, we might care if, for example, not in necessarily an allocative setting, but just in a setting where like we're providing some service, if some groups that are somehow statistically different from others are underrepresented in the population on which you're training a model, the benefits of automation would potentially be unequal. You'd be deploying an inferior product for some people versus for others. There's a question of if you're using, even if prediction were the right thing to do, there's obvious problems that come about if your labels aren't really an unbiased expression of whatever quantity they're supposed to capture. So, for example, if you just want to, even if you thought the right thing to do is to predict sort of who would perform well, just in an observational sense, after being hired at some company based on historical data. If your data is, say, who got promoted, then what you're ultimately capturing to some extent is who does the existing managerial staff or something prefer to promote, potentially encoding whatever sort of systematic perhaps discriminatory preferences they might have. Right, again, there's the problem of even if we think the right task is a prediction problem, often what we end up doing is still optimizing for the wrong task altogether. So I work in medical data a lot. This may be my pet application that I spend most of my applied time in. And I could test here, even if it's not clear that predicting what diagnosis a doctor would give is the right thing to do, but even if you believe that is the right thing to do, but that's not what we have data for. What we have data for is billing codes. But so if you take a look at how these electronic health records are architected, it's all around billing, right? And you don't have often diagnoses, but diagnosis codes. But diagnosis codes are not diagnosis codes; they're billing codes, and you have to bill anything that you do against the diagnosis code. So, for example, this creates weird situations. Like if you need to get tested for a condition that you might have but don't necessarily have, you get the billing code associated with your account because we don't know if you have MS, but in order to run the lumbar puncture and to check for oligoclonal banding, we need to bill it against the billing code for MS. And then if you don't have it, maybe they do or don't remember to remove that from your file. So anyway, right? And then we have all these complications that our data is messy. We often don't know what many of our covariates mean. That's certainly the norm in machine learning. Statisticians or actual scientists are certainly much more concerned usually about what their data actually means, but we operate in a kind of data agnostic way. We don't spend a lot of time agonizing over what real world quantity our sort of measured variables are supposed to represent. And so it's almost like even meaningless to talk about measurement error because we don't even know what we're measuring in the first place. So I want to set this against, and I'm not a legal scholar, so maybe someone here speaking at Center for Ethics would correct me if I'm making any mistakes. But I'll present sort of to my best effort understanding some context in just how the law deals with these things. And I'm going to bring up the law specifically because a lot of the fairness literature invokes sort of legal doctrines and sort of purports to mathematize them. And I just want to actually dig into them. So the sort of bedrock piece of civil rights legislation in the United States that I think is constantly referred to in the context of work on fair machine learning is the Civil Rights Act of 1964, right? And so this is, I guess, a photo of shortly after the ratification. And in the Civil Rights Act of 1964 gave rise to sort of two legal doctrines that arise in sort of the principles according to which we sort of classify or recognize discrimination. The first is disparate treatment. And so what I want to do as we go through these is to call out sort of areas in which there's some aspect of the law that we have absolutely no idea how to, it's clear that it's not a statistical quantity, or certainly clear that we have no idea how to capture it in just some expression of, a joint distribution. So disparate treatment is concerned with intentional discrimination. And keep in mind, the law is not math. So the law does not say, here are some set of axioms that cover every situation you will ever encounter, and this is some general set of principles. The law often is addressing various real-world problems. So there's something like, there's laws prohibiting drugs that we know exist. There aren't laws prohibiting drugs that have not yet been a source of addiction because they haven't been a problem yet, so nobody's bothered to create a law. In the case of just disparate treatment, this is sort of, I think, addressing more bald discrimination. And this, specifically, and this is a weird thing to me, is that, we have so many papers saying that, oh, this is what disparate treatment is, and this is what disparate impact is. The Civil Rights Act of 1964, specifically like, Title VII of the Civil Rights Act is quite short. This is maybe like after lunch read. And the number of people that are writing papers, where this is like your life's work, is saying that you work in this area, that have not read it, that don't actually know what they're claiming to mathematize, is absolutely just flummoxing. And I think we should just be, this is, I think, part of like paper cancer, but I think we should take a hard look at ourselves. Anyone's doing this is like, this is our life's work, supposedly, is doing this research and submitting these papers. And to have, the bedrock of it is some definition of a quantity that stems from like a 3-page document you haven't read, is absolutely just flabbergasting. So disparate treatment addresses intentional discrimination. This includes decisions that are explicitly based on, right? By the way, the Civil Rights Act also formalizes this notion of a protected group. The protected groups that are addressed in the Civil Rights Act are those that I guess people in 1964 were willing to deem worthy of protection. So you see race and gender and age and religion, but you do not see, for example, sexual orientation, even though that sort of factors into the application of the law in some jurisdictions. Right, this includes decisions explicitly based on protected characteristics, but the key aspect of disparate treatment is this word intentional. And I don't know if any of you know how to assess the intention of a classifier or of a system based on a classifier whose behavior is determined by some underlying data collection and objective setting process, but or even to determine whose intention is the one that sort of comes to play there. But it's, this is what we do is we sort of take these definitions and what people do is they sort of ignore the word intention. They'll say, let's just ignore that. Let's just say decisions based explicitly on a protected characteristic and throw out this whole notion of intentionality because we don't want to worry about it. It also includes intentional discrimination based on proxy variables, right? Now, by contrast, disparate impact is a doctrine that is meant to address this problem where facially neutral practices might nevertheless have an unjustified adverse impact on members of a protected class. So the word that I'd call out here that we don't know how to mathematize that gets rounded off is unjustified. What does it mean to be justified as a function of the joint distribution of some observable data instead of classifications? I don't think people even bother to think about it. I think it's let's rule this out. And if you actually look at what's the process, the legal process, and obviously this is a bit United States centric, but this is for whatever reason the U.S. It's the U.S. law to which a lot of this literature is anchored, or at least it's inspiration from that it's anchored. If you actually say what does the disparate impact case consist of, it's a 3-step process. It's a complicated doctrine. First, the plaintiff sort of demonstrates a statistical disparity. This is not the beginning and end of the process. This is step 1 of showing like, hey, we should look deeper. It's sort of cause to launch an investigation. Step 2 is the defendant has to sort of address the specific disparity and show that these are justified, that the disparity arises because, and this requires some normative judgments ultimately about what does justified mean. There's also, I think packed into the word justification is some notion of causality that if you talk about like we're hiring people for some athletic sports team, then you're going to say, well, this is what it takes to win games in the sport. And we're hiring people based on things that are relevant, not in the sense that they have high mutual information, that they're correlated, that these are causally relevant things. You can make a counterfactual statement. Were someone not to have this skill, they could not perform this job, something like that. And then the plaintiff has an opportunity to sort of contest this argument and propose an alternative practice. alternative practice, and this also has a flavor of causality to it too, right? Because an alternative practice seems to me like a counterfactual statement. It is saying here is a different policy that you could have deployed, and an argument that were you to have deployed this alternative policy, you could have achieved sort of the same business end without giving rise to this disparity. This is a very complicated thing, and which I think it's not mathematized in the language of like Pearl's causal inference or Rubin's causal inference, and I don't even think we have tools that we could do that, at the level that I think we need to deal with these things informally. But informally, qualitatively, the kinds of statements we're concerned with do have this causal flavor to them. So let's look at now, I think, like how people in fair supervised learning have tried to address things. And what they basically said is, let's take the standard ML setup, but instead of just having features and targets, feed them into the machine learning algorithm and get out a learned model, let's now somehow incorporate the sensitive feature into the learning process. So, and you say, what should we try to achieve? You say, let's make the groups equal. And the question is, equal in what way? You can draw up an infinite number of different equations where you have some kind of assertion where on the, a conditioned assertion where on the left side of the equation you condition on group membership is in group 1, and on the right side of the equation you condition group membership is group 2. And you could say, well, and so what people say often is say, let's just say that the prediction should be should be sort of like marginally, conditionally independent of, should be independent, not conditioned on anything, of the demographic membership. And so it's basically an equal fraction, like, if some fraction of people from group 1 are assigned to the positive class, presumably being assigned to one of the classes is better than the other, then also the same fraction of people in group 2 should be assigned, irrespective of any kind of consideration of like procedural fairness, any consideration of what's actually involved in making a decision. One of the big dangers here that I'd point out as sort of a side note is one of the ways that things go completely off the rails is that once you start speaking very abstractly about these problems, it's easy to get completely lost because you don't actually think about what actual decisions look like. And one way this became apparent to me was when I was working on admissions. And I'm working on admissions, I say, wait a minute, who's the population? And the population, when you're making a decision, if you're just going to say, hey, people are streaming through some classifier, I've got a data set, for a hiring decision, the population is people who applied. And so actually asserting that the outcome is independent of group status, I think there's a sort of like implicit, I think, normative consideration that people proposing this think what they're achieving is something like the parity with respect to the demographics in the underlying population. That's not what you would get. I think what you'd get is the most anti-progressive policy you possibly could deploy if you demanded this, because you'd undo any attempt at diversifying or kind of correcting for sort of like past wrongs in society. So, once you sort of abstract away from reality, you can look at some of these things and think intuitively, hey, this looks fair, but it might actually be like the very most sort of regressive thing you could imagine doing. What we say is let's have treatment parity, or what they call blindness, but what people in the paper, unfortunately, what people do is they call this disparate impact, as though this just is disparate impact as defined in the law. It's not. But because it's the first step of that process, right, is to demonstrate, say, like it is the mathematization of something like the 4/5 rule, right? And so people just call that, they say, okay, this is disparate impact. And they take blindness, meaning that the classifier just doesn't directly look at the demographic membership, and they call that, this is disparate treatment, or not having, looking at it would be not having disparate treatment. Problem here is that, well, all of your features are correlated with each other, and this sort of made, in the event that you sort of can perfectly reconstruct a demographic membership from you have a sufficiently rich set of other covariates, you've basically done nothing by having blindness directly. And you have a lot of people saying, well, let's solve it with GANs because it's 2018, and why think when you could just stick an adversary in it and do the GAN dance. So they say, okay, let's have an adversary, and let's have the adversary try to not be able to tell the representations apart. But this basically is just saying, this is just a roundabout way of getting demographic parity, right? It's just saying, I'm going to make it so that I can't tell them apart, it basically says, well, if you can't tell them apart, then the same fraction necessarily are going to get classified in each side if you're just applying the same classifier on top of them thereafter. And then you have a bunch of other people saying, a bunch of other sort of like confusion matrix jujitsu, where basically what people do is they look at the different entries and they say we should have equal false positive rates, we should have equal false negative rates, we should have equal false positive and false negative rates, we should, so on and so forth. So what this kind of looks like, right, is we say blindness or, treatment parity says ignore this guy, ignore the sensitive feature, basically produce a model that doesn't directly look at the sensitive feature. Impact parity, as sort of defined in these papers, says, okay, maybe you can look at the sensitive feature, maybe not, but the important thing is that basically you're going to take the outputs of your model and the true labels and the sensitive feature, and you're going to assess some parity condition, whether it's equal false positive rates or equal false negative rates or demographic parity. And basically the idea here is that you're going to use a sensitive feature during training to fit your model. You're going to try to fit a model that satisfies the parity condition, but perhaps at the end of the day you may or may not actually produce a model that relies on those features. So we have as a kind of weird situation where AI people are doing the AI thing, which is taking a bunch of words that they've heard and just assigning them to kind of reductive technical definitions that don't really square up against the underlying sort of like societal issue that they're sort of purporting to address. And here's I want to show you how it can go, like a sort of case study of how this can go catastrophically wrong. And it can not just go wrong, it could go wrong with people publishing papers for many, many years and a whole long line of work that makes, I would argue, no sense without people realizing it because they've backed out so far from a real problem. And so this is a set of, I started seeing a line of work in this area that I identified as disparate learning processes. And I think the first couple times we submitted this paper before it landed in NeurIPS 2018, I think we wound up with some peer reviewers who had written these papers that do this thing, and they were not very fond of the term. But I think this is what they are. This is, I think, a nice functional characterization of what they are. The disparity is in how you do the learning, but you ultimately produce a model that hopefully satisfies some kind of parity condition after the fact. So, right, so there's a bunch of papers. Basically, what they say is, hey, you can't have disparate treatment because the law says you can't do it. But we don't know what disparate treatment really is. So what we're going to look at is, the law is really complicated, right? Disparate treatment doesn't just say you can't have intentional discrimination. And basically, disparate treatment is by definition illegal. And so when the law, which it does sometimes, says that you can incorporate demographic information, say when promoting diversity is considered to be like of national interest, it's by definition not disparate treatment. So the definition here is not the classifier, the decision process is blind. The definition is the decision process is blind and is not intentionally using this information, except for in cases where it's permissible to use it. And what are those cases is of fundamental importance. And if you remove that from the equation of what is the problem I'm addressing? Is this a problem where it is OK to explicitly intervene and say that we believe that promoting diversity is in the state interest? You basically get this glaring disconnect between that and what's going on in ML, where they just say, OK, blindness. So disparate learning process, OK, we're not going to have treatment disparity because our classifier is going to be blind. And we're not going to have outcome disparity because we're going to train our model incorporating a sensitive information at training time, group membership, to fit our parameters such that the resulting model, assuming that our future data has the same distribution as our training data, such that our future data satisfies whatever parity condition. So keep in mind, we've backed out completely of, we have the wrong definitions. We have no idea what problem we're actually addressing. We're describing them in very abstract terms. And we also are not in any way considering the wider scope, which is that the moment that you start deploying these systems, you are not facing the same data distribution, right? What you're doing, as soon as you deploy a system, what you're doing is you're participating in a system of incentives. And as soon as you deploy a new policy, people change their behavior, and the distribution of data is going to be completely different. So, right, problems here is, look, if all the groups were at the very moment, if you lived, and this will kind of tie into our more recent work, making kind of some connections to political philosophy, it's like, you know, this is kind of, I guess, the teaser is that basically, like, there's this distinction between sort of like the ideal approach and the non-ideal approach to theorizing about sort of like justice and political philosophy. And basically, you know, maybe an argument against the ideal approach is basically says, let's just like imagine that we live in a perfect world and everyone's completely compliant and fix some things that would hold in that world and sort of try to have those things be true. And the sort of problem is that it doesn't really give you normative guidance for what to do in the real world that you actually live in. And I think like an argument against the non-idealist would be that like, hey, the ideal approach is sort of a straw man. No one actually believes it so naively. And the answer is, well, some people do. And the people are, it's fair machine learning, I think, is where we actually have the most naive deployment of the ideal approach. Of basically what you said is, hey, well, look, if every group is already identical in every way, then all we need to do is be blind, and everything will be identical about them because they're otherwise, you know, are characterized by identically distributed data. If you live in a world where, for various reasons, historical reasons, people are characterized by different distributions over whatever features we have for them, then you sort of wind up with the fact that like you can come up with a whole bunch of parities that you want to hold, and they're irreconcilable. Like you can't satisfy multiple among them simultaneously. And so you get a cottage industry of impossibility theorem creation. And in ML, we're sort of myopic. And like in stats, people tend to like have a competition of who gets the oldest citation in their paper. And I think in ML, we often, you know, like I've even seen papers that like say like the LSTM from 2014. So we don't even sort of look back, you know, 20 years. But actually, this has happened many, many times, and in economics and political philosophy, and way predating the modern work on fair ML, is that basically you propose a bunch of axioms, and they're irreconcilable. And they're just irreconcilable because, hey, you have two different groups that are differently distributed, and you have a single decision maker that has a single lever, and there's nothing you could do with that single lever that's going to make every single parity condition hold simultaneously. You just don't have enough degrees of freedom. So, you know, basically what we find is we analyze these algorithms, and we find that, like, you know, this is a little bit reductive, but basically, theoretically, you know, if you're trying to reconcile, impact disparity, like if you want to achieve demographic parity subject to maximizing, if you want to maximize accuracy subject to achieving demographic parity, you know, basically not having impact disparity, then treatment disparity is optimal. Like it is at least like in the large data limit. It is the optimal thing to do. Basically, it's real simple. If you believe the probabilities that you have, the optimal thing to do is explicitly just set different thresholds for different groups. You say, the problem with this system is we're not accepting enough people from this group, and we're accepting too many people from that group. Explicitly move the needle. That is actually like the optimal way to trade off the disparity. And it's not just for demographic parity for a number of these. It's just, and there were a few papers, ours was one of them at the same time, that basically just showed that this is sort of a contrived problem. If you just take any one of these things against accuracy, the way to optimize it is just threshold setting. Now, because it's the optimal thing to do, if your other covariates basically reveal the demographic membership, so it's like you could deduce it, or a model in your class is powerful enough to deduce it perfectly with no noise, implicitly, then basically like all you've done is you've got out functionally this same exact model, but now you've taken it from one that explicitly depends on the demographic to one that outputs the exact same predictions for everyone, but just sort of pretends not to depend on the demographic. So then the interesting case is what happens when basically you can only noisily infer someone's group membership from their other covariates. And I'm going to show you what happens, and it's a bit frightening, and I think it kind of shows how if we don't think about even a toy example of what's going on here, we can really confuse ourselves. Is that basically, if you apply one of these algorithms, one of the side effects that you get is you end up like reordering even within a group. So say it's like men and women in both our synthetic and our real data example, is if you apply one of these algorithms, you don't just change you know, who gets, like that you don't just move the needle for, say, okay, we're going to accept less men and accept more women because we care about diversity. What you're actually going to do is you're going to end up rejecting some women who would otherwise be accepted, accepting some women who would otherwise be rejected. You're going to change your sort of like orderings within the groups in weird ways. And also, one of the things that comes out of here is before you at least knew what you were estimating. You said, I was estimating a conditional probability, assuming that like my historical data is like actually some stable distribution. Now, once you start applying one of these algorithms, you have no idea what you're estimating because you're estimating some kind of likelihood objective that is set against a whole bunch of constraints that you don't really understand. And this entire process is being done without any consideration of what actually are the decisions that you're making and how do they interact with the social system that you're putting out there. And one result here is that basically you can create all kinds of bizarre incentives because you're not thinking about incentives at all in the first place that are just truly like, frightening. So here's a toy example, is that we could say, so in this toy example is something like that Alex concocted, and then we'll get to a real example, but just to kind of show qualitatively what's going on. You could say that imagine you have a situation where the only thing that's sort of causally relevant for someone's work performance is their work experience. And for historical reasons, maybe men have had, like, say, access to a certain career for a longer period of time than women had. So there's more men with more experience. So in this case, we have men are the blue dots and blue triangles. Women are the, I guess that's orange dots and orange triangles. And so basically, there's more men over on the right side, more women over on the left side. And then you have, you're doing the normal ML thing, which is you've got a bunch of covariates that don't really matter, but happen to be correlated with your other features. So imagine you have hair length. Now, I don't think someone's actually going to explicitly put hair length as a covariate here, but the point is, as a didactic example, imagine you have hair length. So now, if you basically set some kind of cutoff for who you hire based on work experience, you're going to hire many more men and you're going to hire many fewer women. Now, if you say, hey, we don't want to do that, we recognize that, hey, we are in some kind of point in history where we have some, think that we have some, imperative to intervene in the process and do things in a better way. The sort of natural, stupid thing we could do is just say, okay, we're gonna accept less men and we're gonna accept more women, and we're going to sort of apply some pressure in this process that is going to, lead to a future in which there's more parity among the amount of work experience that people have had. The other thing you could do is you could say, well, I'm going to apply one of these algorithms off the shelf that's basically going to be, whether or not that's what we thought it was going to do in our head, is going to be implicitly trying to reconstruct what their gender is without having access to the gender information, using what other covariates are available. And in fact, it had to be. Like the only way the algorithm could possibly work is if these other features were correlated with gender, without any regard to any consideration, say, of like procedural fairness. Like, are these, or any consideration of the incentive structure. So without any consideration of like, are these features that are relevant in any way? So imagine we have hair length involved, and we apply, this is actually applying the algorithm, this is synthetic data, but actually applying one of these algorithms off the shelf. What you get is, rather than just setting different thresholds for men and women, what you do is you get this new decision boundary, which is the dotted blue line, that says we're gonna, and indeed it rejects more men and accepts more women. So the downward triangles are the ones that are people who had their decision flipped from positive to negative because you applied this algorithm. The up triangles are people who had their decisions flipped from negative to positive. But you notice you have some women who have short hair. So basically the model is implicitly trying to use hair length as a surrogate for gender. So some women with short hair have their decisions flipped from positive to negative. Some men with long hair actually benefit from the policy, which is actually meant to be benefiting women because they happen to have long hair. And you can also step back and think, well, what happens the very next day when you deploy the policy is that everybody goes out and starts growing their hair long. So basically it says, hey, you can be, we're going to help women, but only those women that sort of conform to stereotype in the sense that it's easy to predict, for whom it's easiest to infer their own based on the variables available in our data set. So here's a slightly more frightening example with real data and synthetic discrimination is that we have a data set of 9,000 students who are considered for admission to a master's program of a large United States university over an 11-year period. We have labels, which are admissions decisions, which are basically what did the faculty admissions committee say in the previous year, positive or negative. We have attributes that include gender as our protected attribute, but also things like country of origin, interest area, GRE, and a bunch of other features. And then we apply synthetic discrimination. We just take a bunch of women whose decisions are positive in the data set, and we flip their decisions to negative just to say, in case we believe the people at this university are well-intentioned at the real data. We don't know if there's discrimination in the real data, but we know there's discrimination in our slightly semi-synthetic data because we put it there. So now we could say same thing, only what we're going to do now to make this really clear is what we could do is we can make a plot here. And what this plot is going to show is we've got two axes. And the x-axis, basically, we've trained the model to just, instead of trying to predict, so the natural thing is just predict whether or not the committee would have admitted this person and set a threshold based on that. And that is this black line here, right? That is sort of like the naive machine learning approach. What we do here instead is if we train a model and try to predict is someone use the model to just predict their gender based on their non-protected attributes. And you see, there's sort of a spread here, right? Some people it thinks are very unlikely to be female. Some people it thinks are very likely to be female. And then we also train the model to predict the probability that they're going to get admitted. And what we can visualize is basically if we apply the DLP on this data, we could say who gets their decisions flipped. So this plot over here is the same plot. It's just a zoom on the critical region. And what we see is that the people who have their decisions flipped from negative to positive are people who are thought by the model based on their non-protected features to be more likely to be female and are just a little bit below the threshold. The people who get their decisions flipped from positive to negative are people who the model thinks are more likely to be male and are just a little bit above the threshold before you apply the algorithm. But notice a couple things. One is that there's a number of females who have their decisions flipped from positive to negative. There's a number of males who have their decisions flipped from negative to positive. These are individuals who should have been helped by the intervention that are hurt, or people that should not have benefited from the intervention that do. And then here's where things get sticky, is that what do you think among the features that we had were the things that were predictive of gender? In our case, one of the things that was most predictive was what was your interest area, your stated interest area. So there's the big gender disparities over who wants to join which area. So what does this mean? Now it means that we're going to intervene in the process, and what we're going to do is we're going to take the areas that have the biggest gender imbalance, the areas that most want for diversity, and we're going to actually sort of like we're going to hurt people who are applying into those areas, the areas that actually need the intervention. And then we're going to take areas that actually have a solid balance now, and say that's where actually people are going to benefit because you think because they want to work in that area that they're more likely to be female. So the big danger here is that you could wind up with a policy that actually, because we've sort of lost resolution and thought in this kind of clumsy way about the problem, and we never thought about what is relevant. We never thought about even is this actually what the law mandates, or can we just intervene directly and do something coherent? We wind up creating, because we never accounted for incentives, we wind up creating this really incoherent system that has the potential to cause more harm than good. And I think this has happened many different times in different ways, and people have even constructed very toy models and just tried to zoom out of a simple kind of economics-y type model and say, so I think there's a nice paper from, there's a number of these. I think Lily Hu's done some very interesting work in this area. I think Moore's Hart student Lydia Leo had a Best Paper Award, where there's a number of these papers where they basically step just a little bit back from the classification formulation and say what actually is the impact that we have on the social system if you make what sort of the myopic statistical view, the static view of fair ML says is the right thing to do. You do that, you wind up like in the next iteration. If you actually just account for even the slightest bit of a feedback loop, you can wind up with cases that the intervention that you think is sort of parity promoting could actually be disadvantageous to the group, harmful to the group that you're trying to protect. And And so as predicted and hoped for, I don't have to talk about interpretability today. What I'll end with is that, and this is a paper with my postdoc, he's sort of jointly, I guess, working with a professor in philosophy, and with me, Sina Fazalpour, made this really wonderful connection, and it came from just reading the literature on sort of ideal and non-ideal approaches to sort of theorizing about these questions of justice that has a long history in political philosophy. In this case, this is a book called The Imperative of Integration, which is specifically, right, this is not the first time we've thought about group-level disparities. In the United States, there's a long literature of people wrestling with what is the right thing to do in the wake of sort of America's sort of racist legacy, and what are the right policies. And this book is a book basically advocating sort of aggressive integration promoting policies. And it's nice because, I mean, among other things, you really get to see over the course of a few hundred pages what sort of doing the work looks like, what it actually takes to make a clear argument about what is the justice promoting. And it doesn't mean that everyone's going to read the book and agree with every single claim or every single policy, but you see what an earnest attempt looks like. And I think there's a lot of these. It's been kind of enlightening to spend a good chunk of maybe the last year reading some of the literature in this area. I think some other books that were nice. Ruha Benjamin's book, I think, gives you again, a much broader view. There's a book called Racecraft that I think makes you step back and even think, are we doing something fundamentally wrong by participating in a system of classification that sort of reinforces like race as even a valid distinction, and what are the ways that we can sort of combat these past harms without participating in that. But she talks about it and says, what are the ingredients to actually, and this is at a time when we were like sitting here trying to articulate what was wrong with like this sort of entire way of conceiving of things as just a classification problem. What actually, and this is basically this problem, like we don't have the right ingredients. What are the right ingredients? And Sina started reading way more broadly and made this connection that basically like there was a number of paragraphs here where almost exactly like what we probably better stated than we would have put it, but that capture qualitatively what we were going for, which is like, she says, what do we need? First of all, we need a causal explanation of the problem that we're dealing with in the first place. There's no way to say what is fair without any description of like actually what is the data that you have, what is the societal process that gave rise to it. Like there's no getting around it. Like a lot of people say, okay, but I've got a deployed system and I got to do something. You can't wish away like impossibility. It's like you can't wish away insufficiency. And one thing that I would just kind of inject here is that one thing that's sort of missing in that whole conversation is like what's off the table is people aren't considering that maybe if you haven't done the work, you shouldn't automate a decision. And that there's I think an important conversation that needs to be had about what decisions should not ever, at least not now with what we know how to, should not be automated. And I think a lot of decisions in criminal justice fall into this category that we should be thinking really seriously about whether this technology is mature to play any role in it at present. So right, we need a causal explanation of the problem, determining what can and ought to be done about it. And second, we need to know who should be charged with correcting it. So there's this question of what are the relevant decisions, and actually who are the actors in which decisions that have a responsibility for doing what. And then third thing is that this is a sort of fact-sensitive enterprise that we ultimately, and this is sort of a difference between the ideal and the non-ideal approach. The ideal approach, which I kind of glossed over, is we sort of imagine a completely perfectly just world, and we sort of focus on some kind of discrepancy, some way that our world is different from that, or some way that people make decisions is different from how you would think they would in the ideal world, and just say, okay, well, let's be more like the ideal world. So I think one thing that maybe the ML literature has, which I'll get to, is sort of that may just one thing that's nice about the impossibility theorems is it's sort of a way of, I think, going back to the philosophical problem and saying, well, a big problem in the ideal approach is that this might not actually be possible because there's a question of it might not be possible to minimize all discrepancies, and the relevant consideration is which one, and not how to optimize it. How to optimize it is usually actually a trivial math problem, and that the real problem is what should we be optimizing. But like the classic case, the textbook case of like or this is a case maybe we could disagree, but classic case of like the ideal approach, potentially, I guess I would argue maybe being misguided, is that people would say that what we should do is have a system where we never in any way take into account, you have only colorblind policies, only race-blind policies, and the rationale from the ideal approach is sort of to say, the reason why you should do it is because the perfect world, everyone would be race-blind. And the argument that Anderson makes is that what it doesn't tell us is that it doesn't tell us what, given that we don't live in an ideal world and that we don't have a history of everyone being perfect, and we don't have perfect compliance, it's like, what is the thing, what is the right thing what is the justice-promoting thing to do, given that you live in this world that is not ideal, that does not have perfect compliance? And I think this lens is really important, and I'm really glad that Sina is better read than I am and made this connection. I think this literature articulates it much better than we're doing right now. And I don't think these issues are actually have anything to do with machine learning. It's just that like they're timely because of machine learning, but they've been, I think, discussed, and I think way more than people in the ML community give philosophers credit for. But the second thing, the last part is that it's fact sensitive, that ultimately like a policy is a hypothesis. You have a policy that you believe will be justice promoting or will bring you closer. Like the ideal serves as like maybe a goal, but ultimately you come up with some proposed policy and the ideal just forms sort of like an evaluative standard. But at the end of the day, you have to have some understanding of the mechanisms, not just those that cause the problem, but also the mechanisms by which your proposed policy interacts with the world and either exacerbates the problem or makes it better. So what I'll end with is just, I think this connection is really important. I think this is literature that, I think if the only contribution of the paper is just to maybe expose people in ML to this literature, that is quite relevant. So, I mean, I guess I just put a blob of text because, and now that this is something I always hated in philosophy talks, they have blobs of text, but I just wanted to incorporate this material from the paper and remember what I wanted to talk about. You don't have to read it, but that's always what happens. I think to sum up, like sort of the conclusions here is sort of like, there's a danger right now that like what we're doing in this community is, and I stated this before, is just basically that we're sort of giving the appearance of like an academic certificate of fairness that like inoculates people against regulation or even that sort of takes someone at the Simons Institute, a legal scholar put this really, really well at Cynthia and Patricia Williams at this workshop they organized, said like sort of what we risk doing by virtue of this enterprise is taking like the judge out of judgment. Is that we pretend that we have a technical solution for it, but the biggest danger is that we take out human judgment from the process altogether. We convince policymakers that there exists a technical solution, that we don't actually need someone to like do the work, so to speak. I think also that this gives us a real clear lens on these impossibility theorems, and that I think they become really trivial, I think, when viewed from the ideal and non-ideal lens, which is just that all that the impossibility theorems tell us is you don't live in the ideal world. It's just a frank like certification. It's just saying, hey, it's just a confirmation you don't live in the ideal world. And you are just one agent in it. There's nothing you can do that will make, even by virtue of the limited view of data that you interact with, that will make everything identical in every way. And the takeaway is not this misguided takeaway of like, well, fairness is impossible, or let's just pick one out of the hat and focus on that. The takeaway is that the important consideration is actually what should you be doing, not how do I optimize it. And then Sina, again, being better read than me, did I mention he's on the job market, identifies other source that just absolutely, I should have hid the footnote here, that blew me away, that this is from a book called Equity in 1994, that, basically, if everyone in 2016 read, it says exactly what's wrong here, right? With basically just enumerating axioms of sort of equity. So sort of, basically from simple and intuitively plausible propositions about the meaning of equity, one draws general and sometimes surprising conclusions about the form that an equitable rule must take. The axiomatic method has two weaknesses, however. The first is that while each axiom seems reasonable by itself, when piled on top of one another, they almost inevitably lead to impossibility theorems. This confirms the skeptic's predisposition to believe that the problem had no solution anyway. The proper conclusion, however, is that not all desirable conditions can be satisfied simultaneously. Some choice must be made. And I think maybe this is even more important. A second difficulty with the axiomatic method is that it can easily become disengaged from the problem that it was intended to solve. The invention of axioms and conditions is a fascinating business. The danger is that the exercise can take on a life of its own and lead to results that are mathematically elegant, but have little or no relation to the realities of the underlying situation. And I think that's kind of the place that we've just sort of cycled back to 26 years later. So anyway, I'll end there. You know, the work on disparate learning processes, I think, you know, just as much credit goes to Alex Choldachova and Julian Macaulay, my collaborators, and this connection to the relevant work in political philosophy. I think the lion's share of the credit goes to my postdoc, Sina Fazalpour.